Okay, good afternoon again, everyone. So just some reminders. Homework number 2 is due tomorrow, October 6th, right before midnight, while you already have homework 3 assigned in Canvas. So it will be due on the 11th. So hopefully we'll be finishing today all those things that are necessary for homework number 3. So you can start doing it, or those two problems and the bonus problem associated with homework 3 today. So para yung submission para makasubmit kayo on time on Monday. So here's a quick look at the content of Unit 2. Section 1 is about limit of a sequence. Section 2, limit theorems. Section 3, monotone sequences. Section 4, Cauchy sequences and the Cauchy criterion. And Section 5 will be compact sets. I think in your Math 36 classes, you already kind of discussed sections 1 to 4. So medyo bago na lang dito siguro ay section 2.5. So maybe Unit 2 will be a breeze. So probably we can start discussing. My target is to finish at least section 1 today, but we'll be lucky if we will be able to tackle section 2.2 as well. Oh, by the way, let me just check the poll dun sa kailan yung yung first problem set. I think more than 60% of you said the best time for problem set 1 would be October 15 until 18. So let's finalize that. So let me just put it here. So problem set 1 will be assigned on October 15, 8 a.m. and will be due on October 18, Monday, 5 p.m. So Monday, ito ay Friday. Donnie, you have a question?
Sir, 3 days lang po talaga yung problem set.
Yes. Though dahil over the weekend, so naging 4 days siya. Do you think you need more time? Probably we can do until Tuesday if you want. Will that be better?
Sir, if okay lang po kasi po yung problem set 2 po sa 111, same po ng sked niyan.
Okay. Kaya pala marami rin nagsabi ng nagsagot ng ibang dates. So sige, let's do it Tuesday or Wednesday. Okay lang ba? Or sige, sagad din natin Wednesday. What's Wednesday? October 20th? Hindi ko naman babaguhin yung length. So probably how many items? Probably 4 to 5 items. Yung ibibigay ko. And then so Friday, kung bibilangin natin yung weekend, Friday, Saturday, Sunday, Monday, Tuesday, Wednesday. So you have 6 days. So if you'll be able to answer one problem per day, mapera yung Sunday, so you'll be in a good shape. So okay. Is this better? Is this schedule better? Do you think you can manage?
Sa akin, sir, feeling ko okay na po. Thank you
Okay, how
po.
about that? Yep. You're welcome, Donnie. So ganun lang, kung feeling nyo medyo mabigat or mabigat yung schedule nyo, I can accommodate some of your requests. So yeah. Okay. So if that is fine with everybody, so this is our final schedule. Kaya lang minsan gusto ko maiksi lang yung deadline, maiksi lang yung time frame para hindi na siya para hindi na siya ganon matambak sa schedule nyo. Kasi if you have 5 days, 5 days nyo pa siyang iisipin. So kung matapos kayo ng maaga, that's good. Pero kung hindi, medyo malaki-laki pa siyang dalahin sa inyo academically. So yeah. And then, oh, by the way, I will assign individual bins, submission bins for each item. So hati-hatiin ko siya, problem set 1.1, problem set 1.2 until 1.5 or 1.4. Para pag natapos na kayo sa isang problem set item, pwede nyo na siya kagad i-upload sa Canvas. Tapos para mag-gradean ko na rin siya. So hindi nyo kailangang antayin na tapusin lahat ng problems. Pwede kayo mag-retail submission. So patingi-tingin nyo siyang i-submit sa Canvas, that's fine. And I will greatly appreciate if you do that para nag-grade ko na rin sila paunti-unti na hindi ko naantayin yung matapos lahat, magsabay-sabay sila sa October 20. So, yun. Just one drawback of this long deadline. Siguro after 1 week, magpa-problem set 2 na rin tayo. So, problem set 2, probably 1 or 2 weeks after this, medyo magiging tight yung schedule between them. But I think that is better. All right, so any other concerns about this? Okay, if none, let's go down to business. So the first section is about the definition of the limit of a sequence. And basically, this is the same concept you encountered in, I guess, Math 36 or Math 38. Hindi ko tanda kung alin dun sa dalawa. But essentially, a sequence is a function whose domain is the set of natural numbers to the set of real numbers. By the way, just to emphasize, our set of natural numbers starts from 1, 2, 3, and so on. Some books might start at 0. That's perfectly fine. That's their convention. But for us, let's stick with the set of natural numbers starting from 1, 2, and so on. And then ang sequence is a lang function, right? Pero ang domain niya is set of all natural numbers. So for every natural number, it assigns a unique real number as its value. So this notation means for a natural number, little n, we are assigning the real number a sub n. Okay, so a sub n is called the nth term of the sequence, while is the nth term of the sequence. So usual notation to para dun sa subscript. Now, aside from looking at the sequence as simply a function, right? So meron siyang function, meron siyang domain, meron siyang range. Yung sequence, madalas din nating tingnan as an ordered list of real numbers. So alternatively, or at least on a layman's term, you can say that the sequence is just a list, or actually in particular, an infinite ordered list of real numbers. Okay. So basically, pwede mo siyang tingnan as A1, A2, A3, and so on. It's an infinite ordered list of real numbers. So with emphasis on the term ordered. So kahit naka-set notation siya, when we say a sequence, the ordering matters. Makikita nyo bakit nag-order yung order later. But essentially, the first list is the real number associated with the natural number 1. The second entry in the list is the number that corresponds to the second natural number 2, the third to the third natural number 3, and so on. So merong one-to-one correspondence, a set of natural numbers with the elements of our ordered list. Okay, it's an infinite list. So you cannot write exhaustively the elements of this list. Kasi nga, infinite siya. And it will have infinitely many terms. Kasi ang mga a sabays ang tawag natin sa kanila ay mga terms. However, the range of a sequence might be finite. Okay? So magkaiba yung list of terms at saka yung range. Yung range, remember, ang range ng isang function is the list of possible values of the function. Posibleng may mga sequences na limited lamang yung number of choices for the images. So ilan lang yung options natin para sa A sub n. We will see some examples of that later. Pero ang usapan, infinite list siya, some of which or some of the terms might be identical. Okay? Pero yun, infinite listing siya that is ordered. So some examples are this. Number 1, 1 over n, 1/3, 1/4, and so on. So basically, here we're listing elements of the terms of the form 1 over n. So C1, yung first element corresponds to 1 over 1. Second element corresponds to 1 over 2. Third element corresponds to 1/3, and so on. So basically, sinulat ko lang pala ulit, no? Basically, you can think of it as an equals f of n equals 1 over n. So this is our function whose domain is the set of natural numbers. So if you are more familiar with the math36 definition or the algebra definition of a function, then there you go. So 1 over n. Now, an alternative way, instead of listing the elements, if you can find a general formula for each of the term in the sequence, so you can abbreviate this and write this as simply as a 1 over n, and is a natural number. So this is what we call the set builder notation for our sequence. Okay? So pwede rin namang isulat mo siya in this way. Pwede rin 1 over n. Dahil understood na kapag ka ang context ng pinag-uusapan natin are sequences, understood na itong portion na to. So you can just say n going from 1 to positive infinity. Or better yet, kung talaga nagtitipid ka sa sulat, pwede na lang nating isulat as long as it is clear that we are talking about sequences 1 over n. Okay? Pero dapat clear yung context kasi in a general mathematical discourse, ang basa ko dito ay set containing 1 over n. Pag hindi ko alam ng usapan natin ay usapang sequences pala, right? So be careful if you want to write this, if you want me to consider this as a sequence, either say that it will stand for a sequence, or kung usapan lang naman natin ay puro sequences, then this is fine. I guess the safer notation would be this to denote the sequence, all right? And you see that this sequence is an infinite list. Obviously, for any natural number, you will have a term. And further, it will have an infinite range. Kasi ang range niya will contain all rational numbers or all fractions of the form 1 over n, which is infinite. Okay. All right. Now, as we have mentioned, pwedeng look at number 2. This is an example wherein we don't have a list, but we have a generic formula that stands for the elements of the list, right? Or of elements of the sequence. So to get the first element of our sequence, we simply replace n by 1, all right? The smallest natural number. So when n is 1, we'll have 2 over 1, first element. Second element is when n is equal to 2. So 2, 2, so we'll have 3 halves, and so on. And you see, I am now free to use the terms first element, second element, third element. Because again, sequences are ordered lists of real numbers. So talaga yung ordering nagmamatter. Okay. Okay, going to example 3, posible namang isulat nyo lang ay a sub n. Tapos i-define nyo yung a sub n later. I guess the lecture notes avoided the use of this notation, yung sinabi ko kanina, because we want to differentiate singletons from sequences that might cause some confusion. But yeah, I guess this is another safer way of writing it. Kaya lang medyo mahaba siya kasi meron ka pang where a sub n equals 2 to the n is a natural number. Or, of course, you are not limited to using the variable a as your placeholder. You can use a variable x. An example 4 is one type of a sequence we call a recursive sequence or recursion. A recursion is a sequence whose previous element depends on, whose current element depends on previous elements. So for instance here, we say that, oops, dapat ito ay nasa ilalim. X sub n plus 1 is equal to x sub n plus 1 all over 2. So it tells us to get the next element of the list, yung previous element, kailangan kong dagdagan ng 1, tapos yung sagot, i-divide ko by 2. So yeah, that's an example of a sequence, all right? Or another way of writing a sequence in a recursive fashion. So these are several options para mag-describe ng sequences. Can you guys give me an example of a sequence? Perhaps a famous sequence that you remember? Plus points sa problem set. Oh yes, Donnie?
Sir, yung Fibonacci po.
Okay, great. That's one good example of Fibonacci sequence. Do you remember how Fibonacci sequences are defined?
Yun po ba yung ia-add mo yung dalawang magkasunod, tapos yun po yung magiging kasunod nung number dun sa sequence.
Right, exactly, Don. Thank you. So ang nth term ni Fibonacci sequence, let's call it x sub n, ay equals x sub n minus 1 plus x sub n minus 2, the sum of the two previous Fibonacci numbers or Fibonacci elements or Fibonacci terms. Now, syempre, for the recursion to work, we should give starting values, all right? Para ma-define natin yung kailangan natin ng pagsisimulan or puhunan para ma-compute natin yung Fibonacci sequence. And since the nth term of a Fibonacci sequence requires two previous values, so we need at least two starting values. So the usual Fibonacci sequence starts with x1 equal to 1 and x2 also equal to 1. And again, in a sequence, the terms need not be unique. So here, like in the Fibonacci sequence, the first term is 1, the second term is again 1, and then the next term would be computed as the sum of the previous two. So you can imagine x3 is equal to 2, x4 is equal to 3, x5 is equal to 5, and so on. So ganun yung pagka-compute ng sequences. And you see na kapag you say it's a list, maybe it doesn't make sense to say 1 is the first element and 1 again is the second element. But mathematically, a sequence is a function of natural number, a function whose domain is the set of natural numbers. So definitely, if I give you the number 1, the function value is 1. If I give you the natural number 2, the function value is still 1, which is perfectly valid from a function point of view, right? Kasi hindi naman lahat ng functions ay 1-to-1. Okay, so this is an example of a sequence. Another example is, say, this list. The constant list. So here I have a listing of purely ones. So to convince you that this is indeed a sequence, I will define f of n to be equal to 1 for all n in n, right? So the domain is the set of natural numbers. And again, for every natural number, I am assigning a unique element, which is equal to 1. So ibig sabihin, sequence pa rin to. Although as a list, this might not make any sense because puro 1 lang naman to. Sorry, dapat may dot, dot, dot. Kasi infinite list siya dapat, right? Pero this is an example wherein we have an infinite list containing purely ones. Pero ang range nung sequence is just the singleton set 1. Kasi isa lang yung posibleng value ng sequence. Right? If all terms has value equal to 1. Okay? Okay, now we said that sequence is an ordered list. So the ordering matters because in analysis, we usually don't care about the first few terms in a sequence. Our main concern is to study what happens when n becomes large. Ano yung nangyayari dun sa tail end ng sequence, right? And we put a special name for the behavior or for the value being approached towards the tail end of the list to be the limit of a sequence. Okay, so and that's what definition 2.2 is for. So in definition 2.2, we say that the limit of a sub n as n approaches infinity is equal to a. And we say that a sub n converges to a as n approaches positive infinity. Or we say, probably you can also write a sub n approaches a. Kapag ang context naman natin ay series, automatic na ang behavior na tinitingnan natin is as n approaches infinity. So this is perfectly fine. If it is understood that a sub n is an arbitrary term in a sequence, whenever you write a sub n arrow a, that means a sub n converges to a. Or if n becomes large, then a sub n becomes very, very close to a. So the idea of a limit of a sequence is ano yung nangyayari dun sa dulo ng listahan, dun sa infinite list of real numbers. So we don't care about the first few terms or the first 100 terms, first 1 billion terms. What we're after is the behavior when n increases without bounds. Anong nangyayari? Saan palapit ng palapit yung mga a sub n's habang palapit na ng palapit si n or palaki ng palaki si n. Okay? Now, it seems to be very natural, right? So kung i-graph niyo yung sequence, halimbawa, halimbawa, ito si A1, ito si A2, tapos nandito si A3, nandito si A4, tapos si A5 nandito, tapos si A6 andito, si A7 andyan, and then and so on. Tapos nandito si A99, nandito si A100, tapos nandito na yung ibang mga terms. Okay? So on. Palapit siya ng palapit kay number A. So kapag ka nagcluster o nag-accumulate yung mga A sub n's, habang si n ay palaki ng palaki, malapit na malapit kay A, then we say that the limit of the sequence A sub n is equal to A. Or we say A sub n converges to A. Ano yung value na nilalapitan ng mga A sub n's habang palaki ng palaki si n? It sounds very intuitive. Ano yung nangyayari kapag ka malaking-malaki na si n? However, may problema kung gano'n natin siya i-define. Ano yung ibig sabihin ng palaki ng palaki? Ano yung ibig sabihin ng palapit ng palapit? Tama? Kasi sabi natin, ito yung behavior kung saan palapit ng palapit yung mga function value or yung mga terms sa sequence kay A. Pero how lapit is malapit? Gaano kalapit dapat para mo consider na malapit enough, right? At dapat inoobserbahan natin ito habang si little n ay palaki ng palaki. But how do we quantify being palaki ng palaki? And that's what definition 2 tries to formalize. Because again, in math, we need to be very precise because our business is to prove something without the shadow of a doubt. So ibig sabihin, kailangan clear sa atin ano yung mga definition. So definition 2 tries to quantify yung palapit ng palapit at palaki ng palaki na sinabi natin in the intuitive definition of the limit of a sequence. Now, it says here that for all epsilon greater than 0, there should exist a capital N, a natural number capital N, such that for all little n greater than or equal to big N, then A sub n minus A is less than epsilon. Okay? Try nating himay-himayan bawat elemento nitong definition na to. So let's zoom in into first the absolute value. Sabi natin dapat palapit ng palapit kay A. Now to quantify yung pagiging malapit na malapit, kukunin natin yung distance between the n term and the supposed limit A, right? And that's what is being computed by this absolute value. This is the distance of the n term from the claimed limit, right? A. And we want it to be less than epsilon, okay? Now remember sa math, kapag ginamit natin yung epsilon, it usually refers to a very small number. So we want A sub n minus A, or the absolute value, to be less than a very small number. So that means the distance between AN and A is bounded above or is smaller than a small number. Yun yung gusto nating sabihin ng paliit ng paliit. But gaano kaliit dapat si epsilon? Well, we should be able to do that for any epsilon greater than 0, however small it is. So dapat maging arbitrarily close si A sub n kay A. Pero anong sabi natin? Hindi naman nagmamatter. Medyo pwede natin pagaanin yung definition. Kasi sabi natin, hindi naman nagmamatter yung unang finite number of terms dun sa sequence. Ang concern natin, ano yung nangyayari sa tail end ng listahan. So ibig sabihin, this bound for the distance, though we want it to happen for every epsilon greater than 0, hindi kailangan na masatisfy to ng lahat ng little n's. Dapat lang sa bawat epsilon, sa bawat small distance that you prescribe, we should be able to find a lower bound capital N na kapag lumampas ka na kay capital N, itong distance threshold na to ay nasa-satisfy. So you can think of it as a response, as a demand and response type of definition. Pag binigyan ka daw ng epsilon, kasi arbitrary yung epsilon. Pag binigyan ka ng epsilon, dapat may maibigay ka sa akin na n, na capital N. Na kapag yung subscript little n ay lumampas na sa big N, dapat yung distance between all those A sub n's with subscript greater than or equal to capital N and A, ay dapat mas maliit na kay epsilon. Okay? So dapat makahanap kayo ng minimum subscript na after that subscript, yung distance between the terms of the sequence and the supposed limit ay mas maliit na dun sa error threshold na ibinigay kanina. And you should be able to do this for every epsilon. And that tells us that this capital N is usually dependent on epsilon. So maybe lagyan natin to ng quantifiers. So for every epsilon, however small, kasi again, ang business natin ay sa mga maliliit na epsilon, there exists a capital N, and this capital N usually depends on epsilon. Kasi ang demand ay epsilon, ang response ay capital N. Pag binigyan ko kayo ng isang epsilon, however small it is, dapat makabalik kayo sa akin, ano yung capital N? Na lower bound para dun sa subscript so that the terms after that lower bound is within epsilon distance to the supposed limit. Okay? Right, so you can think of epsilon to be the limit demon na gustong pahirapan yung buhay natin. So the limit demon will give us the epsilon. Hindi kayo yung namimili ng epsilon. Yung limit demon ang magbibigay, ito yung epsilon. Tapos kailangan sa proof mabigyan niyo ako ng capital N para makumbinsi talaga ako na yung limit ay equal kay A. Right? So let's try to look at an example here. Hopefully clear yung definition. Though I know that you might have encountered this before in previous courses, but I just want to emphasize the point. At sabi nga, meta-axiom of ignorance. So ngayon, hindi kayo pwedeng gumamit ng theorem about limit of sequences na hindi natin approved sa Math 155 by the meta-axiom of ignorance, right? So kung may mga fancy techniques kayong natutunan before, hindi nyo pa siya pwedeng gamitin unless in-state ko siya or pinroof, right? Now let's try proving example 2.1. Okay. Ang limit daw ng 1 over n as n approaches infinity is 0. So or in other words, we can say the sequence 1 over n converges to 0. That means habang palaki daw ng palaki si little n, yung 1 over n palapit ng palapit kay 0. And this makes sense, right? Because if you write down the first few elements of the sequence, you see that this is comprised of 1, 1/2, 1/3, 1/4, 1/5, and so on, all the way to 1 over 100, 1 over 101, and so on. Abot ka na ng 10 to the 10, and so on, right? And it's an infinite list with an infinite range. Now, pero nangyayari, palaki ng palaki yung subscript. So, pero yung numerator, hindi yung subscript. Palaki ng palaki yung denominator. Pero yung numerator is a constant. It's equal to 1. So, ibig sabihin, nagdi-divide tayo, dinidivide natin si 1 by a very large number. So, that means really, in the long run, as n increases, yung value ng fraction will be very, very close to 0. But that is our conjecture for now. Intuitively, alam natin na, habang palaki ng palaki si n, yung value ni 1 over n palapit ng palapit kay 0. In this example, we will establish that indeed, the limit of 1 over n as n approaches infinity is 0. And then for the proof, actually, we usually start with the preliminary analysis, or PA. Na kino-compute muna natin ano yung n. Because remember, given tayo ng epsilon, okay, kailangan nating makahanap ng capital N. So in this case, gusto natin na we want to find a capital N such that for all little n greater than or equal to capital N, ano nga ba yung ginamit natin? Less than or greater than or equal to capital N. Dapat totoo tong inequality na to, a sub n minus L less than epsilon. Okay? And this should be true for all epsilon greater than 0. Okay? Yung a sub n term is 1 over n. The supposed limit is 0. So gusto nating makahanap ng capital N na totoo ito. 1 over n is less than epsilon. Because this guy reduces to 1 over n. 1 over n is positive, so nawala na yung absolute value bars. So kailangan ko makahanap ng isang expression involving epsilon and little n. Para kung ano yung makakasatisfy, ano yung capital N that I can substitute for the little n, yun yung pipiliin ko na capital N. Okay? So basically, I want an expression that depends on epsilon. So basically, what I can do is to multiply both sides by what? N over epsilon. So pag minultiply ko both sides ng N over epsilon, I'll get 1 over epsilon less than N. Okay? And here, I can choose capital N. So nakahanap na ako na kapag ka daw si little n ay mas malaki kay 1 over epsilon, then magiging totoo itong inequality na to. Right? Because these are if and only if statements, yung sa inequality. So from here, we can also go upward. So yung kagandahan ng PA, parang dinadaya natin. Nagsisimula tayo dun sa gustong conclusion para makahanap tayo ng boundary. Okay? So ibig sabihin, magiging totoo itong inequality na to kapag si 1 over epsilon ay mas maliit kay little n. So here we can choose big N to be something less than 1 over epsilon. Okay? Kasi actually hindi pala less than, dapat ay greater than 1 over epsilon. So ibig sabihin, pwede kong piliin si capital N na mas malaki kay 1 over epsilon. So basically what I just did is to replace little n by capital N. Kasi sure na ako na si 1 over epsilon ay laging mas maliit kay little n. So if I will let big N to be greater than 1 over epsilon, then the previous statements will still apply. Okay? So usually ito yung first step sa proof. Naghahanap tayo ng capital N para sa isang given na epsilon. Okay? And now, to write the formal proof, we just need to work backwards. So for the formal proof, okay, remember sa proof, dapat sa kahit anong given epsilon. So we start with assuming a specific epsilon or a generic or an arbitrary epsilon. So here we say given an epsilon greater than 0. No other restriction on epsilon basta greater than 0 siya. Okay? So given ang isang arbitrary epsilon, kailangan makapagbigay tayo ng capital N. Na kapag ka si little n ay mas malaki or equal to capital N, then a sub n minus L will be or the absolute value will be less than epsilon. All right? So pero alam ko na yung option ko or what's the appropriate or what's a nice choice for capital N. So here I will choose capital N to be equal to 1 over epsilon. Or you can say something, you can also say greater than 1 over epsilon. Okay? Pero ano yung requirement? Dapat si capital N ay natural number, right? So definition, there should exist a capital N. But can we always find a natural number that is greater than 1 over epsilon? Kasi pag sinabi ko na si N, dapat ay mas malaki kay 1 over epsilon. Now, what guarantees that this N exists? So maybe I can say choose N natural number such that N is greater than 1 over epsilon. Okay. Now, ano yung nag-guarantee sa akin na may nag-exist na natural number capital N such that it is greater than 1 over epsilon for any given epsilon? Any volunteers? Or baka naman wala. Pag nagbigay ba ako ng random na epsilon, lagi bang may nag-exist na natural number na mas malaki kay 1 over epsilon? Do you guys remember a result that guarantees that? Padali, pag nag-recite plus problem set. Pero raise hand muna bago mag-chat or mag-unmute. Para matrack ko kung sino yung nagsagot. No takers? Oh yes, Christine.
Ano po, ang nag-guarantee po sa atin na merong capital N greater than 1 over epsilon is Archimedean property po.
Thank you, Christine. Yes, it is the Archimedean property that guarantees that there always exists a natural number that is greater than 1 over epsilon for whatever epsilon greater than 0 is given, right? Thank you, Christine. By the way, dun nga pala sa mga nagre-recite, kindly put a comment on the chat na nag-recite kayo kasi dun ko siya itatali. I already commented Christine's name kasi hindi pa yata siya member ng MS Team. So, yeah. Okay, so yeah, I can note here the existence of which is guaranteed by the Archimedean principle. Okay, then for all epsilon, so for every little n, so whenever we have a little n greater than or equal to n, then what can we say? Then 1 over n will be what? 1 over n, which is also the absolute value of 1 over n, which is also 1 over n minus 0, is less than or equal to 1 over capital N. Right? Parang baligtad. Hold on. Okay, hindi ko siya pwedeng isulat ng ganito. All right. But anyway, we have 1 over n. Okay. But we have chosen capital N. Oops. But we have chosen capital N to be greater than 1 over epsilon. So ibig sabihin, kung si kung si capital N o si little n ay mas malaki or equal kay capital N, so therefore, valid pala yung sinulat ko kanina that this is true, right? Kasi mas malaki si little n kaysa kay capital N, so that means 1 over little n would be smaller than 1 over capital N, right? But what do we know about capital N? Capital N was chosen to be greater than 1 over epsilon. So in other words, this tells us that epsilon would be larger than 1 over capital N, which is basically yung kabaligtaran ng preliminary analysis. So we know that 1 over n is smaller than epsilon. We have 1 over capital N here. So this would be less than epsilon. Since we have chosen capital N to be something that is larger than 1 over epsilon. Okay. And basically we have a sub n minus L being less than epsilon. So that ends the proof that indeed the limit of 1 over n is equal to 0 as n approaches infinity. Okay? Again, ang challenge dito, pag binigyan kayo ng epsilon, dapat mapakita nyo na may nag-exist na capital N. Okay? Any questions on that? Wala naman so far. Let's try another example. Let's prove that the sequence AN with AN equal to root of n plus 1 minus root n converges to 0. Okay. Of course, it usually pays to look at specific instances of these sequences in order to at least have or to be convinced that at least by looking at several examples, the sequence AN really converges to 0. So ito yung sequence, o ito yung terms dun sa ating sequence. So when n is equal to 1, so we have root 2 minus 1. If n is equal to 2, we'll have root 3 minus root 2 and so on. Pero pag palaki ng palaki si n plus 1 at saka si n ay napakalapit na sa isa't isa, right? So especially when n becomes very, very large because their difference anyway is still equal to 1. And so when we subtract the square root of two numbers that are very close to each other and n is very large. So in other words, we're subtracting two large numbers from each other that are close to each other, then we expect the answer to be close to 0. Okay, kaya we know that the limit is really equal to 0. Okay? Now to prove this, we'll do a PA first. Kasi nga, ang goal natin, pag binigyan ako ng epsilon, dapat makahanap ako ng capital N, which is a natural number. So let's try a PA, do a preliminary analysis, and discover ano kaya yung appropriate choice for capital N. So we want to find a big N, natural number, such that for all epsilon greater than 0, okay, we have this a sub n minus 0, which is basically root of n plus 1 minus root n is less than epsilon, okay? Whenever little n is larger than or equal to big N. Yan yung goal natin, makahanap ng capital N that satisfies this statement. So let's play with this inequality. And then let's try to have epsilon on one side and n to the other side para makita natin ano yung appropriate choice. Now, let's manipulate this first. Okay? So yung absolute value ng root ng n plus 1 minus root ni n, dahil mas malaki si n plus 1 kaysa kay n, yung root ng n plus 1 ay mas malaki sa root ni n. So this difference is always positive. So to make our analysis easier, I can just get rid of the absolute value bar. Okay. And then medyo nakakagulo yung square root. So basically, one trick I can use here is to multiply this guy by something equal to 1. Any suggestion? Ano kaya yung trick na gagamitin ko dito? Ano yung pwede kong pang multiply top and bottom na equal kay 1 para ma-simplify itong expression na to? Or to get a nicer form for this expression. So this multiplier is something equal to 1. So basically it's a number over a number, number over itself. Any suggestion on what expression that would be? Oh yes, Carlo.
Sir, I forgot the term, pero conjugate yata yung term. Yung baliktad lang yung sign ng first
Okay.
instead ng minus plus.
Okay, great,
Yung-
Carlo. So yeah, yung conjugate nung radical expression. So which is basically root of n plus 1 plus root of n. And you will see later why this will work. Ito yung mahirap sa real analysis o sa advanced calculus na ginagawa. Kasi usually may mga expressions kang dapat na isingit out of nowhere para mapadali yung analysis. Unlike sa algebra, wherein usually pag alam mo yung definition, magfa-follow through yung proof, right? Pero sa calculus or sa real analysis, medyo kakaiba. Kailangan maging creative ka dun sa choice of expressions to add inside your proof. So for instance, in this expression, in this proof, or in this to this expression, I need to multiply it by the conjugate over the conjugate. And that will not change the equality here kasi itong expression na to ay equal lamang naman kay 1. But the nice thing is, if I multiply the numerators, so this guy times this guy, they would be conjugates of each other. So kung ito ay a minus b, tas ito ay a plus b, so ang product niya lang ay a squared minus b squared. So basically n plus 1 minus n, which will just simplify out to 1 over root of n plus 1 plus root n. Okay? And we want this expression to be less than epsilon. Okay? So ito yung final goal, makapag-bound para kay epsilon. But what do we know about this expression? Pasimplihan pa natin. So we can say probably that what? Maybe we can say that this is smaller than, would you agree? This is smaller than 1 over root n plus root n. Kasi pag pinaliit natin ng pinaliit yung denominator, mas lumalaki yung fraction. Pag tinanggal ko yung plus 1, mas malaki na sa denominator, magiging mas malaki na yung resulting fraction. Right? And then I can simplify this into 1 over 2 root n. And we want this to be less than epsilon. Okay, so here I can say we want 1 over 2 root n to be less than epsilon. Okay, and then to attain this, I want to know what the value of little n should be. Ano dapat yung lower bound dun sa value ni little n so that this inequality will be true. All right. So what I can do here is to first square both sides of the inequality. So I'll have 1 over 4n less than epsilon squared, okay, which is fine. And then I will multiply both sides by n over epsilon squared. So I'll have 1 over 4 epsilon squared less than little n. So this means that if we will be able to make sure that little n is not larger than 1 over 4 epsilon squared, then this inequality will be true, right? So kapag si little n ay mas malaki kaysa kay 1 over 4 epsilon squared, then magpa-follow etong inequality na to. And this is the beauty of doing a preliminary analysis kasi sa formal proof, ito lang yung pipiliin kong capital N, or I will choose capital N to be larger than 1 over 4 epsilon squared. Kasi nga kapag si little n ay mas malaki dito, sure ako na mag-hold yung gusto nating inequality. Okay. So here, therefore, we can choose capital N to be greater than or equal to 1 over 4 epsilon squared. Hindi ko pwedeng gawing n is equal to 1 over 4 epsilon squared because I am not sure if 1 over 4 epsilon squared is a natural number. Again, remember that the requirement is that n is a natural number. Kasi epsilon pwedeng fractional. Na yung 1 over 4 epsilon squared will not end up to be a natural number. And remember, n is the lower bound. So pag pinalaki ko yung lower bound, mas okay. I don't need the minimum value for capital N. Basta n is large enough. Sorry. Basta si n ay large enough, then yun yung then okay tayo sa proof, right? Kasi yung n simula sa kanya nagiging totoo yung inequality. So I can choose n to be super large. It doesn't matter basta after niya totoo yung inequality. Okay? Now let's formalize our arguments into a proof. Dagdag lang ako ng page. Okay. So let's write the proof. So again, you always start your proof with given an epsilon greater than 0. Okay. Gusto na kasi nating ipakita sa kahit na nung epsilon greater than 0, laging may capital N. So if we are given an arbitrary epsilon greater than 0, we choose n to be a natural number. With this property that n is greater than or equal to 1 over 4 epsilon squared, the existence of which is guaranteed by the Archimedean property. So I'll just call the Archimedean property AP. Okay, sabi ni Archimedean property, there will always exist a natural number n, which is greater than 1 over epsilon. It just so happened that here, epsilon is equal to 4 epsilon squared, which is perfectly fine. Change of variable lang naman yun. Okay. So if this is the case, then for any little n greater than or equal to capital N, we have this inequality. So we want to show that square root of n plus 1 minus root n will eventually be less than or equal to, will be eventually less than epsilon. But here we know that this guy is also equal to 1 over root of n plus 1 minus root n. Okay. Alam natin equal to via the preliminary analysis. You just need to multiply this guy top and bottom by root of n plus 1 minus root of n. So, siguro lagay natin yung sa proof para kung nakalimutan yung isama yung preliminary analysis, you'll still be good. So ito ay equals sa root ng n plus 1 minus root n times root ng n plus 1 plus root n over the same thing. Okay, and then that simplifies to this. Sorry, mali pala. Plus dapat itong ilalim. Okay, and then this guy is less than 1 over 2 root n. Tama? Nakita na natin to, na-argue na natin to above, right? But 1 over 2 root n would be less than epsilon. Bakit tayo sure na less than siya kay epsilon? Kasi si n, si little n, mas malaki sa 1 over n. So therefore, si little n ay mas malaki kay 1 over 4 epsilon squared. So ibig sabihin, this guy will be smaller than 1 over 2 root of 1 over 4 epsilon squared. Okay. Again, the reason there is since little n is larger than or equal to capital N, which is larger than 1 over 4 epsilon squared. All right. So dahil si n, pinalitan ko ng isang number na mas maliit sa kanya, the fraction becomes larger. The new fraction becomes larger. Okay. And then if we simplify this, this will just become 1 over 2 times 1 over 2 epsilon. The 2's will cancel each other out, leaving us with 1 over epsilon, which is equal to epsilon. So in short, we have proven that the absolute value of root of n plus 1 minus root n is less than epsilon as desired. So that ends our proof. Okay. So yeah, those are just examples of using the definition to prove that the sequence converge to a given value. Okay. Now, any questions on that? Siguro nakapagawa na kayo ng mga ganitong, nakasagot na kayo ng mga ganitong problems before sa lower calculus courses. So you just need to recall some of them. Okay, so that's proof for convergence. And I think the next question is, how do we prove that a certain sequence does not converge to a given number? So let's look at the definition of divergence here. So a sequence that does not converge is said to be a divergent sequence. So if it doesn't converge, then it is then it will diverge. Okay. So we say that the limit of a sub n is not equal to a if and only if there exists a certain epsilon naught greater than 0, such that for all natural number n, there exists a little n greater than or equal to capital N, such that the absolute value of a sub n minus a is greater than or equal to epsilon sub 0. So ito yung negation lamang nung nasa definition. Remember, ang definition natin ay for all epsilon greater than 0, there should exist a natural number n greater than, which is a natural number, such that for all little n greater than or equal to capital N, this inequality is true. Para masabi na ang limit niya ay equal kay A. Now, kung ang limit niya hindi equal kay A, then kailangan lang nating i-negate etong statement na to. And remember from Math 101, how do we negate predicate with multiple quantifiers, right? So nangyayari lang yung negation, pumapasok siya dun sa mga quantifiers. So instead na for all epsilon, there will exist a specific epsilon, and we just called it epsilon sub 0, such that papasok uli yung negation dun sa there exists dun sa second phrase. So such that for all natural number n in n, okay, and then papasok na naman siya dun sa for all na pangatlo, so or pangalawang for all dun sa definition. So there exists a capital N greater than or equal to n, such that papasok din siya dun sa predicate mismo. And then negate yung predicate, so you have absolute value of a sub n minus a is greater than or equal to epsilon sub 0. So in essence, to show that the sequence doesn't converge to a number a, then we need to show na may nag-exist na epsilon greater than 0, such that sa kahit anong capital N, lagi tayong may makikitang little n na mas malaki kay capital M, such that yung a sub n ay lampas sa epsilon naught distance mula kay a. Alright? Now to illustrate this formally, so we look at this example. So we want to prove that the sequence an with an equal to -1 to the power n does not converge to 1. Or actually, it doesn't converge anywhere. Okay? So it's easy to see that hindi siya pwedeng mag-converge kasi if you will expand this list, you will get -1, 1, -1, 1, and so on. So you will see that the terms in the list will just alternate between -1 and 1. At hindi natin alam kung ano nangyayari sa dulo ng listahan. Kasi hanggang sa katapusan, nagpapalit lang siya from -1, nagiging 1, and so on. So hindi talaga natin alam, or actually wala talagang behavior o specific behavior dun sa dulo ng list. Alam lang natin, nagbabaliktaran sila. Pero we don't know, or actually there is no single behavior being approached in the tail end of the list. So for instance, gusto ko ipakita na ang limit niya hindi equal kay 1. So kailangan ko magpakita na may nag-exist na epsilon naught. So in this example, kinuha kong epsilon naught ay equal kay 1. Kasi kapag kasi epsilon naught ay equal kay 1, sa kahit na anong natural number, may makikita kong little n. And that little n is 2 times n plus 1. So baligtad ngayon. So ngayon, epsilon yung given. Gusto kong ipakita na nagiging mali yung inequality sa isang little n. Right? And that little n I used in the proof is 2n plus 1. Gusto ko siya ay maging odd. Right? Hindi ko pwedeng piliin ng even. Makikita natin mamaya kung bakit. Actually, instead of little n, pwedeng sabihin nyo ay n equals actually, kailangan pala si little n ay dapat mas malaki kay capital N. So I can choose any odd number greater than capital N. Okay? Kasi makikita nyo na yung an minus 1, si little n ay odd. So ang odd term, so kapag ka odd si n, yung an ay magiging -1. So this guy will be replaced by -1 minus yung gusto nating ipakita na hindi niya limit, which is 1. So we'll have -1 minus 1. So equal kay 2 na mas malaki kay 1. So nakakita tayo ng isang natural number little n, which in particular would be the odd subscripts greater than or equal to any given capital N, such that the distance between the n term, the little n term, and the supposed limit here, 1, is greater than the epsilon naught that we chose earlier. So lagi tayo may makikitang little n na mas malaki, na mas malayo kay 1, hindi mas malayo kay 1, na ang distance mula kay 1 ay mas malaki dun sa epsilon naught. So that means the limit is not equal to 1. Kasi nakakita tayo ng term na nasa halos dulo na ng sequence na hindi nagiging within 1 yung distance mula kay 1. Right? So that means it's impossible for the limit to be equal to 1. Actually, you can also show that the limit is not equal to -1. Kung gusto nating ipakita na yung limit ay hindi equal kay -1, we can still choose epsilon naught to be equal to 1. Tapos ano kaya yung choice of little n? I can choose little n to be an even number, right? Kasi kung gusto kong ipakita ng limit ng an ay hindi equal kay -1 as n approaches infinity, so gusto kong ipakita yung an minus -1 ay greater than or equal kay 1, which is my epsilon naught. So ito yung epsilon naught. Okay. So kapag ka si n ay pinili ko si little n to be a very large even subscript, so this will become 1 plus 1, which is equal to 2, greater than or equal to 1. Okay? So ibig sabihin, merong mga elements dun sa dulo, specifically those occurring at very large even subscripts, na yung distance mula kay -1 ay mas malaki kay 1. So hindi naging arbitrarily close yung mga elements on nung list dun sa tail end ng ating listahan compared to 1 or -1. So indeed, the limit is not equal to 1 nor -1, and actually it will not be equal to any real number aside from -1 to 1. So it's impossible for that sequence to have a limit. Kapag ka ang limit ay, kapag ka ang sequence ay walang limit, ang tawag natin sa kanya ay isang divergent sequence. All right? So here we'll continue and look at some fundamental results for limits. The first result that we want to prove is that the limit is unique, if it exists. Kasi nga merong mga sequences na hindi nag-exist yung limit. Yun yung mga divergent sequences. But we know that if the limit exists, then automatically it must be unique, right? Pero to prove that, kailangan ko yung isang lemma. I will include it as lemma 2.1. Wala to dun sa module, so dun sa lecture notes. So dagdag natin siya. Again, I will upload I will update the lecture notes to include these additions that we made today. So ano yung lemma 2.1? So it says that if you have a real number x, if the absolute value of x is less than epsilon for all epsilon greater than 0, then automatically si x ay equal kay 0. Which kind of makes sense, right? Kasi itong inequality daw na ito ay totoo sa lahat ng epsilon greater than 0. So kapag meron kang isang number ng absolute value niya ay mas maliit sa lahat ng possible positive numbers, however small they are, then automatically x should be equal to 0. Okay? So nagme-make sense naman yung theorem, right? So, o yung lemma. So let's try to write a formal proof para magamit natin siya. And I will do a proof by contradiction. So suppose x is not equal to 0. All right? So classic proof by contradiction. I-assume natin na false yung conclusion. Gusto natin ipakita na hindi pwedeng mangyari yon kasi magkakaroon tayo ng contradiction to something that was proven to be true before, or something that we already know to be true. Okay. Now, if x is not equal to 0, then absolute value of x over 2 is also greater than 0. It's not equal to 0. In fact, it must be greater than 0. Tama? Kasi daw si x ay hindi 0. So yung absolute value niya ay positive, right? It's greater than 0. Pag dinivide ko yung isang number that is greater than 0 by 2, then the answer is still greater than 0. Agree? And then the statement says, yung premise ng theorem or ng lemma, says that the absolute value of x is less than epsilon for any epsilon greater than 0. And here we have a number that is greater than 0. So this can take the place of epsilon. So if epsilon is equal to root of x over 2, which is valid, kasi yung premise totoo daw siya sa lahat ng epsilon greater than 0, this guy is greater than 0, so I can take that to be the value of epsilon. Then absolute value of x will be less than absolute value of x all over 2. But this is a contradiction, right? Meron kang isang number na hindi equal kay 0, hindi siya pwedeng maging mas maliit sa kalahati niya. Agree? Kaya meron tayong contradiction. A number cannot be less than 1/2 of itself. Okay? So therefore, hindi pwede na hindi siya equal kay 0. Therefore, we must accept that x is necessarily equal to 0. And I think madalas natin gagamitin itong lemma na to. So kaya kailangan ko siyang idagdag sa lecture notes. And this will make the proof of theorem 2.1 a lot easier. Okay. I hope the proof of lemma 2.1 and its spirit makes sense. Okay. Now jump tayo sa theorem 2.1. Yung limit daw ng sequence, kung mag-exist siya ay unique. Again, we can use a classic proof by contradiction here. So suppose that AN converges to A and AN converges to B with A not being equal to B. So kunwari, nagko-converge siya sa dalawang magkaibang numbers, A and B. Okay. Then let's try to find a contradiction. Then for all epsilon greater than 0, kasi nga nagko-converge siya kay A, nagko-converge siya kay B, so pwede natin gamitin yung definition ng convergence o ng pagiging limit kay kay A at saka kay B, right? So if you're given any epsilon greater than 0, then there exists an n1, or let's call it n sub A, and n sub B that are both natural numbers, such that for all little n greater than NA and little n greater than NB, then we have the following inequalities. We have absolute value of AN minus B minus A is less than epsilon over 2, and absolute value of AN minus B is less than epsilon over 2. Well, this is fine kasi dun sa definition, remember sa definition ng limit ng sequence, totoo siya dapat sa lahat ng epsilon greater than 0. Alright? Pero kapag ka si epsilon ay greater than 0, dapat si epsilon over 2 ay greater than 0 din. So dapat may mahanap pa rin tayo na natural numbers, say n sub A and n sub B, such that these two statements are true whenever little n is greater than NA and little n is greater than NB. Okay? So ginamit ko yung epsilon over 2. Makikita nyo mamaya kung bakit gusto kong gamitin si epsilon over 2. Bakit hindi na lang epsilon yung ginamit ko rito? And actually, this is a clue na I have to add something related to these two guys para pag nag-epsilon over 2 plus epsilon over 2, maging totoo tong statement na to. Okay? Now, I will let capital N to be the maximum between N1 and N2. Okay. So for all little n greater than or equal to capital N, the new capital N, which I know is larger than both N1, is greater than or equal to both N1 and N2, then equations 1 and 2 will hold. Right? Kasi ito, totoo kapag kasi little n mas malaki kay n sub A. Ito ay totoo kapag kasi n mas malaki kay n sub B. Pero si capital N, pinili ko to be the maximum between N1 and N2. Dahil siya yung maximum between N1 and N2, kapag ka si little n ay mas malaki kay capital N or equal to capital N, that means little n is larger than or equal to both N1 and N2. So si equation 1 at saka si equation 2 sabay na nangyayari. Before, we don't know if sabay silang nangyayari. Kasi para mangyari si 1, dapat mas malaki kay NA. Para maging totoo si equation 2, si inequality 2, dapat si little n mas malaki kay NB. Pero ngayon, inassume ko na si little n mas malaki dun sa maximum ni N1 at saka ni N2. So therefore, mas malaki si little n parehas kay NA at saka kay NB. So that means both of these two guys are true. Okay? Now let's see what is the absolute value of AB. Okay? So I can rewrite the absolute value of A be as the absolute value of A minus AN plus AN minus B. Ito na naman yung beauty ba or curse ng proof sa real analysis. Lagi ka na lang may ini-insert or madalas meron kang ini-insert o ini-invento ng mga bagay-bagay. So here, we have absolute value of A minus B, pero gusto kong pahirapan yung sarili ko at least on the next stage. Instead of this difference, isusulat ko siya as this guy, which is still equal to the previous guy, kasi ito lang naman at saka ito, they will cancel each other out. So we'll be left with A minus B. But the nice thing about this is I can take advantage of the two inequalities we have above, which we know will be true for all n greater than capital N. So by the triangle inequality, I can separate this into two absolute values. First one is absolute value of A minus AN. The other one is absolute value of AN minus B. Then I can reorder the first inequality, say write it as AN minus A, and this is AN minus B. Okay? And then we know that equation 1 holds. Ano sabi ng equation 1? Si absolute value ni AN mas maliit kaysa kay epsilon over 2. So pwede ko itong palitan ng something that is smaller than itself. Say epsilon over 2. Yung pangalawang term, pwede ko ring palitan ng something na mas malaki sa kanya. So something na mas malaki sa kanya, epsilon over 2. So bawat isang addend, pinalitan ko ng something na mas malaki sa kanila. So the sum that I get is larger than the previous value. And then if you add epsilon over 2 to epsilon over 2, you'll get epsilon. Okay. So in short, we have shown that the absolute value of A minus B is less than epsilon for all epsilon greater than 0. And then by lemma 2.1, dahil mas maliit siya sa lahat ng positive numbers, then A minus B must be equal to 0, or that's equivalent to saying that A is equal to B, which is a contradiction. Because we earlier assumed that A is not equal to B. Right? So hindi pwedeng mangyari na si A ay hindi equal kay B, and at the same time si A ay equal kay B. So there must be something wrong with that supposition. So we need to accept that the limit is unique whenever it exists. Right? Okay. Any questions? Clear ba so far? Marami akong sinasabi, so baka mas napapagulo ko yung idea. But I hope this is making sense. Okay? Tahimik na naman kayo, no? So, yeah. Any questions on that? Maybe we'll end here at theorem 2.2, unless you have questions. Yeah. Try kong tapusin yung 2.2. No questions with the preceding things that we did? Okay, if none, then let's proceed. So some definitions first. Definition 4, a sequence is bounded if there exists a positive number n such that the absolute value of an is always smaller than or equal to m. So geometrically, ibig sabihin, bounded yung mga terms ng sequence, so yung absolute value ng ating sequence, ibig sabihin, yung elements ng ating sequence will lie only on an interval negative m to m. Kasi yung absolute value ng lahat ng terms ay mas maliit sa isang constant m. So that means, if you will expand this using things you learned from algebra, ibig sabihin nito ay si an ay nasa pagitan lamang ni minus m at saka ni capital M. That's why it follows na lahat ng terms ay confined sa interval negative m to m. Kaya siya tinawag na bounded. So hindi siya lumalampas dun sa closed interval. Nakakulong siya dun sa interval negative m to m. Okay? And a nice result tells us that, or probably before that, some examples of bounded sequences, say the sequence 1 over n is bounded. So can you give me a bound? What is capital M for this sequence? Anyone? For bonus points? Ano kaya yung capital M para sa 1 over n? Kasi para ma-prove na bounded siya, kailangan bigyan niyo ako ng capital M. Come on guys, bakit walang gustong sumagot? Alam niyo yung sagot eh. Carlo, tingnan ko lang kung may iba pang sasagot kasi nakapag-recite ka na. Anyone else aside from Carlo? If none, then go ahead, Carlo. What do you think is an upper bound? Or what is a bound?
Sure, yung upper bound niya is 1.
Okay, great. So you can choose 1. Kasi yung absolute value ng kahit anong 1 over n, remember n is just a natural number. So this will be less than or equal to 1 for any n in n. Okay? Well, you can also say m equals 2, m equals 3, m equals 4, or anything larger than 1, that's fine. Because the bound m is not unique. Hindi siya necessarily least upper bound. Basta makahanap ka ng isang positive number that will bound the absolute value of all of the terms in the sequence, then automatically you say that the sequence is bounded. And there's a nice property about a nice property of convergent sequences, and that is summarized in theorem 2.2. Every convergent sequence is bounded. It says here that if the limit exists, then a sub n is necessarily bounded. Let's try to see the proof. Okay. So ang assumption natin ay nag-exist yung limit. So assume that an converges to a number a. Kasi part ng assumption natin na nag-exist yung limit. And we want to show that an is bounded. Or equivalently, there exists a capital M greater than 0 such that absolute value of an is less than or equal to big M for all n in n. So ito yung goal nating mapakita. Okay. So kailangan nating i-construct, or one way to prove this is to construct what capital M is. Okay. So let's take advantage of the fact that we know that the limit is equal to a. So we can use the epsilon definition here. So then, given an epsilon greater than 0, there exists a capital N in n, such that for all n greater than or equal to capital N, alam natin na yung absolute value ng an minus L ay less than epsilon. Okay? Ito yung gusto ko. Pero gusto ko makahanap ng capital M. So kindly observe how I will construct capital M. So here, I will use triangle inequality. Or one version of the triangle inequality. Ang absolute value ng an minus absolute value ng L ay less than or equal to the absolute value of an minus L. Okay? So this is one of the versions of the triangle inequality. But we know that this is less than epsilon. So pwede kong i-continue yung inequality this way. And then in summary, we have this guy is less than epsilon. So I can say, oh, this implies an minus absolute value of L is less than epsilon. And then I can add the absolute value of L to both sides. So I can say an minus an is less than absolute value of L plus epsilon. Okay, so this is true for any epsilon greater than 0. So we take, we can specify this. So we choose epsilon to be equal to 1. So that means there exists an n, capital N, such that absolute value of n is less than absolute value of L plus 1 whenever little n is greater than or equal to capital N. So laging yung mga an ay mas maliit na sa limit plus 1 kapag ka si little n ay mas malaki ka na kay capital N. Pero gusto ko makahanap ng bound na capital M. But that capital M must work for all ANs. Ang problema ko dito, pwede na sana itong capital M. Kaya lang nag-work lang siya kapag ka si N ay mas malaki kay big N. Eh ang limit dapat, ang bound dapat mas malaki sa lahat ng A sub N. Ito, upper bound lang siya kapag ka si little n ay mas malaki kay capital N. So, what do you think would be a nice choice for big M? Disqualified na to so far. Or hindi tayo sure na totoo to na upper bound siya sa lahat ng A sub N. Upper bound lang siya kapag ka yung N mas malaki na sa capital N. Pero ano yung mangyayari kapag ka mas maliit na kay capital N? So what would be my choice for N, for M? Okay. Dahil medyo kulang na ako sa oras, okay, i-reveal ko na yung sagot. I will choose capital M to be the maximum between, or the maximum among the absolute value of A1, the absolute value of A2, and so on until absolute value of A capital N, and then absolute value of L plus 1. Kukunin ko lang yung pinakamalaki sa set na to. Kasi alam ko, pagka lumampas na ako kay capital N, yung mga A sub N's hindi na lumalampas kay limit plus 1. So, ibig sabihin, gusto ko lang makita ano yung pinakamalaki dun sa first capital N terms. Kasi hindi ko alam kung ano yung bound para sa kanila. Alam ko lang after A capital N or A sub capital N, lagi nang mas malaki kay limit plus 1 yung magnitude. Or mas maliit dun sa absolute value ni L plus 1 yung magnitude. So if I will force the issue, or if I will choose M to be the maximum among these numbers, sure na ako na yung makukuha kong M ay mas malaki sa lahat ng absolute value ng A sub N. Right? So then, clearly, ang A sub N ay mas maliit kay M for all N in capital N. Again, the reason why I cannot choose this to be my M right away is because I am sure that this guy is always larger than the magnitude of all of the N terms in the sequence whenever little n is larger than capital N. Para maging boundary, dapat totoo siya sa lahat ng little n. Pero para so kontrolado ko na nangyayari kapag lumampas ako kay A sub capital N. So ang problema ko na lang yung mga first few terms. In particular, lahat ng yung first capital N terms. So pag kinuha ko yung pinakamalaki sa kanila, tapos kinompare ko with the limit plus 1, sure na ako na yung makukuha kong maximum among them ay mas malaki na sa lahat ng A sub N for all natural number N. Okay? And that ends the proof. Kasi nakahanap tayo ng capital N, so we can say that AN is bounded. So lahat ng convergent sequences ay bounded. Now, maybe I can leave it to you as a food for thought. Bakit kaya hindi totoo na kapag bounded siya, convergent na siya? Can you think of a bounded sequence that is not convergent? Sige, may 3 minutes pa naman. Anyone who can give me an example na false yung converse? So sabi ng theorem, kapag daw siya ay convergent, automatic na siya ay bounded. Pero merong mga bounded sequences na hindi convergent. Can you give me an example? Bounded na sequence pero hindi convergent. Para ma-conclude natin na false yung converse. Again, all this theorem is claiming is that kapag convergent yung sequence, automatic bounded siya. Wala siyang sinasabi about bounded sequences being convergent or not. Yes, Rexter, can you give me an example of a bounded sequence that is not convergent?
Yung alternating po na 1 and -1.
Okay.
Bounded po siya ng 1 and -1 sa baba taas, pero di po siya convergent.
Okay, great. Thank you. Because here, tama si Rexter, itong sequence na to na nakita natin kanina, if you take the absolute value of all the ANs, ano yung upper bound sa kanya? You can say an upper bound niya ay 1. You can say upper bound niya ay 2 or anything larger than 1, right? So bounded siya, pero na-prove natin kanina na hindi siya convergent. Okay, thank you, Rexter. Anybody else? Meron pa ba kayong ibang naiisip? Sayang naman yung bonus points, oh. Wala na? Actually, ano pa ba? Wala na akong madaling sequence na naiisip. Let's see, alternating. Siyempre, pwede rin yung -2, -2, -2, -2, -2, -2, and so on. Alternating pa rin sila pero walang limit. Bounded siya pero wala siyang limit. Okay? Okay, so I think we'll stop here. Yung mga nag-recite ngayon, aside from Christine, Carlo, and Rexter, paki-comment dun sa meeting chat. I think may isa na lang nakalimutan. I think it was Donnie. Tama nga ba, Donnie? Ikaw yung nag-recite na isa.
Yes po.
Okay, so sino pa ba? Meron pa ba? 4 lang yung nag-recite ngayon, so you'll get some points sa problem set. Okay, so if there are no more questions, then I think that's it for today. So I hope you guys will enjoy the rest of the night, and then we'll see each other again on Thursday. Bye, everyone.
Thank you.